So with that, let's begin. We want to say something, like I said, about limits involving infinity today. Notice all the problems from the homework and in the warm-up today, and in our lesson yesterday, we're all dealing with infinity never popped up anywhere ever, right? So we want to think about how that might apply if that comes out either as part of the question or part of the answer. Either one could happen in today. Let's review just from what we did too. Remember, right now, where are we at with limits? We have an opportunity to plug it in, right? We have to be a little cautious about that, as we've seen. That's not always a foolproof thing, but if we have an idea of what the function behaves like, then maybe we could just plug it in. We may need to do some algebra first, like you did on the warm-up here. Didn't you have to do one on the warm-up like that? Yeah, here. Over here, D on the warm-up required you do a little bit of algebraic work ahead of time. And then, of course, if need be, especially if you have access to a graphing calculator for a given problem, we're definitely going to come to times when we might want to analyze it numerically, looking at the picture or looking at table values or whatever else. So I've got two for you right now to review a little bit. And the second one will introduce something we'd like to talk about today a little bit. So, and the first task might be, even without a calculator, can you even figure out what that graph for A looks like? So if you haven't thought about that before, it might take a second. Realize what that looks like. Go ahead and answer those. Take a second. A and B. So what would you say there? Can someone, without answering the questions, actually, can someone just describe the picture for A, and I'll ask someone to describe the picture for B, just from your PRECALC knowledge and from playing around with that first function. It's maybe not one that's super familiar to us, but Josh, you want to explain the first one? What does that look like?
With A, when x is positive, then y equals 1. When x is negative, y equals 1.
And importantly, what about at 0? What's going on there?
0?
Yeah, it's undefined at 0. Yeah, we haven't settled on what we think of 0 over 0 in math here. So, yeah, I think that's a good description. Did someone else want to describe what B looks like? Yeah, go ahead.
So, there's an asymptote so that 2 and comes from infinity, going from 2 to the right, comes down from infinity, was on the last one.
Yeah, you can like draw pictures in the air. That's fine. Right? Yeah, exactly. Yeah. It's like, yeah, it's just our reciprocal function moved 2 to the right, with a vertical, or like Peter said, it has a vertical asymptote at x equals 2. So I'm trying to think, do I have a picture of, I don't think I have a picture of that one yet here, but the first one, by the way, is sometimes actually is important enough that, and it comes up enough in math, even though it might not have come up very much in your life yet. That has a name. It's called the signum function. Sometimes it's just called the sign function, S-I-G-N, like the sign of the number. Because basically the only thing it returns gives you give it a number, and it basically returns either a 1 or a negative 1, depending on what the sign of your number is. S-I-G-N, right? So it actually turns out to be a somewhat useful function, even though it seems kind of silly. There are times when it would be necessary. Okay, now I have to actually answer the question. So for A, given that it looks like what Joshua described it as, what would your answer to A be? Yeah, 1. Again, even though it's not defined as 0, we don't care about what f of 0 is actually, whether it is defined or here in this case it's not defined, but who cares? From the right, it's 1, and if we had asked you from the left, it would be negative 1, of course. And then how would you answer B? Is there, what would we say there? You said there's a vertical asymptote there. So maybe we just need to say that it doesn't exist. And can we justify why it doesn't exist? Well, in terms of trains from yesterday, if you want to do trains, what might you say? I don't know. How can we? It's different. It kind of fails to exist for a different reason than we talked about yesterday a little bit, but yeah.
Oh, I'll just like,
Go ahead.
so like the limit from the right side doesn't equal the limit from the left side, so you can't say there's an overall limit.
Yeah, and maybe we could if they were equal in some sense. I know we're already in weird territory with infinity, but we'll say more about that in a second. Just to go back to what Peter said, yeah, there is a vertical asymptote there, and this is, I'm just actually, seriously, at least from my pre-calc class, I'm copying and pasting this from my pre-calc class. So just to remind you that this is the definition of a vertical asymptote, right? Is if the limit from the left to right, now it's a little bit circular because we haven't defined what the limit is, but, and either one of these could be true, right? Like you think of a log graph, you only have asymptotic behavior on one side, but that's okay. It's still a vertical asymptote. If either one of these things holds, then we have a vertical asymptote at x equals a. Right? If the right-hand limit or the left-hand limit go off to positive or negative infinity, then we're good. We got a vertical asymptote. So I think I'm right that none of your homework problems, the answer to none of them was like infinity last night, right? Or negative infinity. That won't be true tonight. You're gonna have some problems that the answer will be negative infinity or something like that. Okay, so let's talk about rational functions again. Here we're back to just plain old 1 over x. So just as a chorus, what's the answer to that one? From the left, 1 over x, what's the answer there? Negative infinity. From the right, positive infinity. And so, you know, it's similar to what Stephen said. What can we say about the overall limit? It doesn't exist. So there's the picture here. So I'll write those out here, the things you just said. Are you okay with D any does not exist? Okay. And there's the picture, of course. There's the vertical asymptote highlighted. What about this guy? What can we say there? I think, was that one of your function library ones? Didn't we have that one on there? So you should know right away what the graph looks like in your mind, right? Yeah, I think we can this time actually maybe say that the overall limit, or you could actually, I should have probably written this out 3 times again, right? The left limit is positive infinity, the right limit is positive infinity, and the overall limit, I think we can say, is positive infinity. So when possible, we want to be as descriptive as possible, right? We want to say it's infinity or negative infinity. Here it's not possible to say that, though. It's a little weird to say like infinity equals infinity on the left and right, but we'll go with that. I want you to start thinking, though, again, it should be kind of like a little bit unsatisfying to just be like, well, it feels like, you know, this seems a little wishy-washy. Maybe we can start working on thinking about a formal definition for what we mean by a limit equaling infinity at a particular value x equals a. So I want you to like think about what demand would you make on someone if they make that claim? They're like, well, I don't think that it is infinity for 1 over x squared. How would you prove that? Yeah, it is. I promise it is. What demand would you make on the function? You think about it. I'll give you the answer to that at the end of today's lesson. Okay. I thought I'd save the details for the end just today. It didn't go so well yesterday with the middle. So I'll save it for the end. Yeah. 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 All right, and don't write this down necessarily, but I do want to just remind you. Now I'd like to think about the end behavior discussion again, and I don't have much to say about it because you've already done those. I recognize that in your library of functions, you've already done a lot of these. So just mainly a reminder of some of the things you know. Certainly, if you're faced with a polynomial function, I think you can not only handle it, but you can also generalize every case that could ever come to you in terms of polynomial end behavior. Same with rational functions. I'd like you to recall in a second. I have a couple examples that will help us recall what you know about the end behavior of rational functions. You can maybe even think about some of the things you've thought about there. Exponential functions. I want you to recall some of those general rules about how that works. And then what about other functions too? Obviously, we don't want to restrict our attention to only those functions. Logarithmic functions have some interesting answers to questions like you would have had in your library of functions. For almost every trig function, the answer is like doesn't, you know, NA or undefined, doesn't exist or something like that. Except arctan is kind of interesting. The arctan inverse trig function for tangent. What might you say there? Also arccotangent, I guess, too. What's the limit as x tends toward infinity for arctan, or for the limit as x goes for negative infinity? The answer to that too. What is it? You know? It's not infinity. We'll keep moving. If you come up with it, let me know. Yeah, on the right it's pi over 2, and on the left it's negative pi over 2. Yeah, it's a very pretty graph actually, compared to the other arc trig functions. It's a really nice, defined for all reals, pretty graph. Yeah. And again, I want to ask you though too, we've spent a lot of time, even in PRECALC and in your library functions packet, thinking about end behavior, but what would it mean for us to come up with a formal definition of that? And I'd like you to think about that too. And what would you demand of someone if you were like, well, I think the arctangent approaches pi over 2 as x tends toward infinity. Okay, neat. Can you prove it? Like, what demand would someone place on you if they were asking you to be rigorous in proving that? And think about it. We'll give away the answer later. Okay, just as a matter of review, this should be review, I think. We're going back to PRECALC here for a second. I've got 4 rational functions here. And I'd like to think about the following limits. I'd like to have, so 2 questions for each one here. I'd like to ask what the limit on both sides is. So take a second, and if you need to talk at the table, you can. But in a second, we'll just write up the answers. Just be careful about what you see happening. They all do look very, very similar, don't they? But there are little changes to each one. So be careful as you go through and answer those. See if you can remember what you've learned from PRECALC. Why did I highlight the yellow part there, by the way? Like, it doesn't really matter at all. So. No. Yeah, I did actually, yesterday I uploaded a couple, but the one I did, but yeah, I haven't put it on. Yeah, I'll upload all my videos.
Yeah, I know. You know that
Did I give you enough time to deliberate yet here? You're still heated debate over there. Yeah. You're right. Everyone thinking, talking. Okay, we're good. All right. So here, let's get some people involved here. Katie, give us the answers, both the answers, left and right on the first one, if you will. What did you guys come up with back there? They're both 0. I think we'll just write equals 0 then. It's the answer to both questions. And did you want to say anything about why that's true or what? Yeah, bottom heavy, yeah, exactly. And again, someone just told you these rules at one point. It would be worth like pushing on that. This is math class, and obviously everything in math is meant to be like a sense-making. This is like a sense-making discipline, right? So you want to make sure you can press on that. Think, well, why does that work exactly? So I would challenge you to think about that. it's certainly true, and I wonder, is it really true that we can just be cavalier and cover this up? If so, then this function is really just 5 over 2x, isn't it?
No, because that changes what happens between the
I'm just saying it has in some ways it has the same end behavior as 5 over 2x, though, right? Like if we really can ignore this, so you might want to kind of think about that. To what extent can I ignore that? I don't know, but I mean we get the right answers if we do, I guess. So maybe we'll go with it. So Vash, do you want to give the answers to this? How about we go over here? This one here. So yeah, so what do you want to say then? Okay, positive infinity, and that's as x tends toward infinity. What about toward negative infinity? Is the same?
Yeah.
Did you guys talk about this one? I don't know. So for the limit as x goes. Is it the same? Is it the same? Or what is it? What happens when you plug in like negative 1 million? What do you get here?
still.
Amy, you want to help us out? Negative infinity? Okay, yeah. I know this is maybe not a question you really thought about very much, so it's okay. Again, you might think if we can again, this takes maybe some proof underneath the hood here. Maybe you're not comfortable with this, but doesn't this have the same kind of end behavior as 5 halves times x cubed? Yeah. I mean, in some senses, I've just like would turn this into a polynomial, right? If we block that, it's like similar. Okay, that's an interesting thought. It's not necessarily like asymptotic to that graph. I don't know. I have some questions about that, but it certainly feels that way. Okay, we have some. This is always going to be. This first term is always going to dominate, and it's positive. This one's going to be negative, though. So, yeah, it's a little tricky, right? Max, what about this guy here? 5 over 2, and is that your answer on both sides, or you want to split that out? Both sides is right. Yeah, you guys with us so far? And then what about this last one here? Again, tell me on both sides here. I know I've already heard from you. Don't want to talk to me here. Christina, what did you say there on the last one?
Limit as x approaches infinity.
Okay, and so as x approaches positive infinity,
Or no.
Careful.
Is it negative infinity?
there's some
Negative
things
infinity.
happening down
The
here.
denominator is negative, right?
Okay, and is that, and then is it different on both sides? Do I need to split this out? I don't know. I'm asking you. So that's negative infinity? What about, is it different for the left side? You guys thought this was going to be easy for this. It takes a little bit of work. You're just on the spot here, maybe. What's the limit as x goes to negative infinity? John is really excited about this. Go ahead.
So if you think about it, like you can think about it as the second graph, like flipped over the x-axis.
The second graph, this one up here?
Yeah.
Except for this thing, right?
Right. Sort of. A lot.
Yeah, there's a square there. That does make a difference, doesn't it? It really is a different animal
It
completely.
really is a difference.
It really is. Charlotte's excited about this.
Well, if you like ignore the highlighted part and then you like simplify it, then it's negative 5 over 2 times x squared. And since it's an even polynomial, then like both ends go in the same direction. Oh, negative.
Yeah. Charlotte's like, yeah, okay, I just cleaned this place up. Okay, I'm out. Yeah, that's good. That's right. Absolutely. Yeah, we just have to be careful. I know a lot of you are just thinking quickly about them, and maybe you need to stop and slow down and think about them a little more. Okay. Again, the definition, copy and paste from your pre-calc course. There it is, of a horizontal asymptote too. Obviously, that's a related concept to when we're thinking about end behavior. So we want to like come out and maybe say what that is. And we can, again, it's an or, right? These, for a rational function, it seems maybe to be the case that if you have a horizontal asymptote on one side, then you have it on the other. Okay, but is that always true? I mean, do we demand it be true on both sides? And the answer is no. That's why we have the word or there. But this particular slide doesn't provide an example where that's happening. That's why we need another slide. I'm here for you, though. Okay, anything you want to stop and talk about on this slide still? About end behavior of polynomials, of rational functions, excuse me. I mean, that was fun, I thought, right? Okay, why is there Buzz Lightyear there? I can't. Oh yeah, that's right. To infinity and beyond. Yeah, that's right. Okay, there we go. Sometimes just this is, you don't need to write this down necessarily, but sometimes we get infinity as an answer when we go out to infinity. Sometimes we get a number. Could be either. How about some more that aren't rational functions this time? Let's do a couple of these, just to get a. And this is not meant to be necessarily crazy. In fact, again, these I think are some of the ones you had in your functional library or something similar at least, right? So just take a second to go through and answer those. People just do those by sight, maybe even easier than the last one. And last. Give 1 second what they think. Still review a little bit, right? Should be. Are you thinking about the formal definitions of the things I asked you to think about? Keep thinking. Alvin, what's the answer to the first one? Where are you, Alvin? Oh. I know, it's a little harsh. Albert, what's the answer to the first one? Agree? Agree. Grace, that was you. You're right. B, how about? Huh? 1? Is that what you said? Yeah. 1. Agreed? Hold the phone, yeah? Oh, it might be 0. Okay. All right. Kira? That's okay. Grace, we still love you no matter what. Kira, where are you? What about C? What did you say there? Say it one more time. Infinity. Yes. Slowly, but infinity. Yes, right? You guys agree? I mean, eventually, we do get to infinity. Good. And then what about D? Yeah, maybe Browning base, maybe something that's an official math symbol. Okay. It doesn't approach negative infinity at all. Like, there's not even anything to say. It would be fine to say D and E there. I think that would be an okay thing to say, too. I didn't want to show you that yet. All right, so in the last 5 minutes, I would love to put in front of you. So most of that was review, I think. I mean, there's a little bit of technicalities there, and but let's see if we can come around the formal definitions just of the vertical, like the when can we claim that f of x, the limit as x approaches a of f of x equals infinity? What do we demand if you claim that it goes off to infinity? I claim, someone might claim, I say it doesn't show me a place where, it, like, I wouldn't, if you're claiming it goes off to infinity, shouldn't you be able to show me a place where it goes beyond 1 million for y? How would you get beyond 1 million for y? If x equals a is the vertical asymptote, what would you have to do? Well, I mean, we don't even know what the function is yet necessarily, but how do we get close to it? I mean, how do we get close to 1 million for y? What do we have to do with x? You make x get bigger? We're talking about a vertical asymptote here. X equals a. Yeah, we need to get close to the vertical asymptote, right? So, in general, now then that should not just be true for 1 million. It should be true that if you bring me any number, that I should be able to find a distance away from x that I can stay within that puts me above your number. For for every number you give me. So with that in mind, that's what this says, okay? This is like the technical definition of a limit at a point here. We can say this, and by the way, I didn't provide you the definition where it goes to negative infinity. It'd be the same thing, it's just like reverse the sign of this and the direction and all that, okay? This is not something that's ever gonna be tested. I just want to put this up here. And I copied this off the internet, so there you go. And it will be on the internet soon too, so. I'd rather you understand it. You can just make sure you understand it here, because I think it's interesting. Again, this is the key part. If for every number m greater than 0, if for every positive number that someone can challenge me with, I can give you a delta such that if we're delta within a distance within delta from x equals a, then that makes this true, right? Isn't that what this says? That's really what we mean if we're claiming that some limit is infinity at x equals a, isn't it? We're saying that no matter what bar you place, I can find a place close to a every time, close to x equals a. Within delta, I can provide a delta that will put us above that y value that you wanted me to be above for every m that's provided. Now, I didn't type up the limit to infinity one, so let's just draw it here real quick, okay? Okay, so if I claim that some function eventually settles down and goes to 0 or something, what do you want? What challenge do you want to put for me there? What's the thought around that? Yeah, you want like my claim is that like this gets close to 0. We want to like we want to formalize that. Go ahead, Jonathan. What were you going to say? Yeah, so if you come up, you say, okay, you claim it's 0, the limit as x goes to infinity is 0, then show me a place after which it always is within 0.01 of 0, right? You hear what I'm saying? So a challenger comes along and puts two horizontal lines on the graph and says, okay, doesn't work there. Is there a place after which it stays within some tolerance above and below the claimed limit? And if I can demonstrate some number n after which, for every epsilon you could possibly give me, that after n, for some n value, that my function always stays within your epsilon limit. No matter what epsilon you give me, then I've established the limit. You with me on that? Okay. So I just think that I don't think we've ever said this kind of stuff to you. So like I said, I didn't type that one up, but you could probably write it right. So again, not anything that AP will ever test, but I just think it's good. You're going to be dealing with limits all year, and it's like good to have this conversation, I think. So it's just good for you. It's like your vegetables. Homework 2 will be checked tomorrow, and I love you all. Was that not a good like what? I do.
I know it's behind the